So sometimes all we need to do is indicate a certain direction. And to do that, we can use a unit vector, which is a vector with a magnitude of 1. So all we use it for is to indicate a direction. And the most common unit vectors are the ones that point along the axes. The I unit vector points along the x-axis, the j unit vector points along the y-axis, and the k unit vector points along the z-axis. And so we distinguish a unit vector from a regular vector with this little hat on top of the letter. And so we can rewrite any vector in terms of its components using unit vectors. So say we have some vector A, and let's say the x component of the vector is 5, and the y component of the vector is 3. So instead of writing this vector A, so we can write this vector as 5i plus 3j, because 5i is just a vector that points along the x-axis with a magnitude of 5. And likewise, 3j is just a vector that points in the y direction with a magnitude of 3. So 5i represents the x component of the vector, and 3j represents the y component of the vector. So now we're going to look at different ways to multiply vectors. And you'll come across two main ways. The first one is called the scalar product, or the dot product. So the scalar product of two vectors produces a scalar quantity. So the scalar product is the magnitude of A, the A vector, multiplied by the component of the B vector that is parallel to A. So if the angle between the two vectors is theta, then the component of the second vector that is parallel to the first vector is going to be equal to cosine of theta multiplied by the magnitude of B. And so we can write the scalar product as AB, the magnitudes of A and B, multiplied by cosine of theta, where theta is the angle in between the two vectors. And so the scalar product can be a positive or negative scalar quantity. And what determines whether it's positive or negative is this angle theta. So if theta is in between 90 and 180 degrees here, like in this picture, then the cosine of that angle will be negative. And so the scalar product will be negative as well. And for the scalar product, the order does not matter. In other words, it is the commutative property holds. So A dot B is the same thing as B dot A. So we can think of it as the magnitude of A multiplied by the component of B that is parallel to A, or the magnitude of B multiplied by the component of A that is parallel to B. And so we can figure out the scalar products of the unit vectors. So any unit vector dotted by itself is going to be equal to 1. Because, of course, they're pointing in the same direction, so all of it is parallel to the other one. And so the magnitude, the cosine, the angle will be 0, so cosine of 0 degrees is just 1. So, but if we dot two vectors which are perpendicular to each other, so any unit vector dotted by a separate unit vector, then the angle is going to be 90 degrees, and cosine of 90 degrees is 0. So the dot product of any perpendicular vectors is going to be 0, because of course, if they are perpendicular, none of the second vector is parallel to the first vector. And so in terms of the components of two vectors, we can write the dot product of A and B as just the magnitude of the component, the x components multiplied, plus the y components multiplied, plus the z components multiplied. And to figure out how we got this formula, we got it like this. So first we have in vector A dot unit a vector B. And so we write them in terms of their components using unit vectors. Now we have AXI plus AYJ dot BXI plus BYJ. And then we just use the distributive property to write out all the terms. And we get this. So as you can see, here we have I dot I, and here we have J dot J. And any unit vector dotted to itself is equal to 1. So these are just going to be equal to 1, and we keep these terms. Whereas any two unit vectors that are different dotted with each other are going to be equal to 0 since they are perpendicular. So these two terms in the middle cross out, and we just have these terms, ax bx plus ay by. So obviously this is only for vectors with an x and y component. If you include the z component as well, then you'll get this formula. And so the second way to multiply vectors is the vector product or the cross product. And instead of producing a scalar quantity, this produces a new vector, which is perpendicular to both A and B. So to find the magnitude of the vector product, it is just the magnitude of A multiplied by the component of B, which is perpendicular to A. In other words, AB sine theta, where theta is the angle between A and B. And also, unlike the scalar product, when we're doing the vector product, theta is always the smaller of the two possible angles between A and B. So to find the direction of the new vector produced by the vector product, we use what's called the right-hand rule. So you take your right hand and you point your index finger in the direction of A, the first vector, and then your middle finger in the direction of B, and then if you hold your thumb perpendicular to both your index and middle fingers, your thumb will point in the direction of the vector product. So to see how this works, you can look at this picture. So A is pointing in the x direction, and B is supposed to be pointing out of the page in the z direction. And so remember, the vector product is always perpendicular to both A and B, so it is pointing in the y direction. So you can see kind of how the right-hand rule works. So to find the vector products of all the unit vectors, we have to define the direction of the positive z-axis. And so we say in a right-handed coordinate system, which is what we're going to be using, I cross j is equal to k. And you can verify this using the right-hand rule. And you can also find the cross products of all the other unit vectors using the right-hand rule. And you can write the cross product of two vectors in terms of their components using this formula. And you get this big messy formula by doing a similar process where you write out the components and then you use the distributive property, and then you have to calculate the cross products of all of these unit vectors. So I'm not going to do that in this video. So the last thing you need to know is that the commutative property does not hold for the vector product. So A cross B is not equal to B cross A. The magnitudes of the two cross products will be the same, but the two vectors will point in opposite directions, because of the right-hand rule.